Welcome back to part 2 of the static timing analysis series. In the previous video, we focused on the combinational logic and learned how to identify timing paths and calculate their delays. Today, we're going one step further by introducing the second building block of every synchronous digital design, the flip-flop. We will learn the timing characteristics of a flip-flop and see how they affect the timing requirements of the entire system. Let's get started. Before we move on, let's quickly review what we learned last time. We introduced two important timing parameters of the combinational logic: propagation delay, the slowest path through the combinational logic; contamination delay, the fastest path through the combinational logic. Combinational logic includes components like logic gates, multiplexers, decoders, encoder, and many other digital circuits. In this video, we will connect these delays to the flip-flops that launch and capture the data. A flip-flop has three important timing parameters. Setup time. Setup time is the minimum amount of time the input data must already be stable before the active clock edge. Think of it as the flip-flop saying, "Give me the data a little before the clock arrives." Hold time. Hold time is the minimum amount of time the input data must remain stable after the clock edge. In other words, don't change the data immediately after I have captured it. Clock to queue delay. Clock to queue is the delay between the active clock edge and when the flip-flop produces valid data at its output. Unlike setup and hold, which are requirements of the capture flip-flop, clock to queue delay introduced by the launch flip-flop. These three timing parameters are the missing pieces we need to perform timing analysis. Timing constraints. Now that we know the timing parameters, let's see how they are used. Timing constraints define the timing requirements that every timing path must satisfy for the circuit to operate correctly. There are two fundamental timing constraints. Hold constraint. The hold constraint checks whether the data arrives too early. To satisfy the hold constraint, the launch flip-flop clock to queue delay plus the fastest delay through the combinational logic must be greater than or equal to the hold time of the capture flip-flop. If the data arrives too quickly, the capture flip-flop may capture the wrong value. An important point to remember is that hold analysis does not depend on the clock frequency. Setup constraint. The setup constraint checks whether the data arrives too late. To satisfy the setup constraint, the clock period must be greater than or equal to the launch flip-flop clock to queue delay plus the slowest delay through the combinational logic plus the setup time of the captured flip-flop. This constraint determines the minimum clock period, which also determines the maximum operating frequency of the design. If you found the video valuable, I'll appreciate your support by subscribing to the channel. Whenever analyze timing, you generally follow these three steps. Step 1. Check the hold constraint for every timing path. Make sure no path is too fast. Step 2. Check the setup constraint for every timing path. Determine the minimum clock period required for each path. Step 3. Choose the system clock frequency that meet the constraints for every timing path in the design. Let's go back to the example from part 1 and add the setup time, hold time, and clock to queue delay for each flip-flop. We will start by checking the hold constraint for flip-flop 1. The hold time requirement of flip-flop 1 is 8 nanoseconds. The data leaves flip-flop 0 after 3 nanoseconds of the clock to queue delay and then travels through the fastest path, which has a contamination delay of 3 nanoseconds. That gives us a total arrival time of 6 nanoseconds. Since 6 nanoseconds is less than the required hold time of 8 nanoseconds, the data arrives too early, and the hold constraint fails. To fix this example, we will replace the capture flip-flop with one that has a small hold time requirement. Now the hold time is 4 nanoseconds. The clock to queue delay and the contamination delay remains the same, so the data still arrives after 6 nanoseconds. Since 6 nanoseconds is greater than the required hold time of 4 nanoseconds, the hold constraint now passes. In a real design, hold violations are usually fixed automatically during implementation by inserting delay buffers or adjusting the routing. In this example, we are changing the flip-flops simply to make the concept easier to understand. Now let's check the setup constraint. For the path from X to D1, there is no launch flip-flop, so we only consider the propagation delay of the combinational logic. That means the clock period must be at least 5 nanoseconds. Now let's look at the path from Q0 to D1. The data first spent 3 nanoseconds inside flip-flop 0 before it appears at the output. It then travels through the slowest combinational path, which is 5 nanoseconds. Finally, the data must arrive 3 nanoseconds before the next clock edge to satisfy the setup time of flip-flop 1. That gives us minimum requirement clock period of 11 nanoseconds. Since we must satisfy every timing path, we choose the largest requirement clock period, which is 11 nanoseconds. Now that we have checked both the hold and setup constraints, we can choose the system clock. The minimum clock period required by our design is 11 nanoseconds. That means the maximum operating frequency is 90.9 MHz. So any clock at or below 90.9 MHz will satisfy all the timing requirements of the design. In this video, we assume clock to queue is a single delay. In reality, it actually has two different values: clock to queue contamination delay and clock to queue propagation delay. In the next video, we will learn why they exist and why one is used for hold analysis while the other is used for setup analysis. Thank you and see you at part 3.